Okay, so three lines cross, they are called concurrent. The point where they cross is the point of concurrency. So over the next four, hold on. There you go. Over the next four, we're going to talk about four different points of concurrency that we have. And specifically, we're going to be looking inside of triangles, different points of concurrency. So they're going to be very similar to each other. So we got to stay organized. That's why we have the notes that we have. All right, so let's start with that outline. Let's take a look at what we can fill in at the start. We are talking about perpendicular bisectors today, which is good because we just talked about those yesterday. So we remember what they are. Right? Perpendicular bisectors, it's through the midpoint and it's perpendicular. We're on page 310 here. In the next column, we're drawing a picture. Okay, so I'm going to have that picture on here for you. It's a little intense, there's a lot going on, but if you look, what we have is we have three perpendicular bisectors drawn here. Right? For each side of the triangle, we have it at the midpoint. So each half, right? These are the same, and so on. And then it's perpendicular through that midpoint. So I want you to go ahead and copy down that figure as best you can. And then we're going to talk about our point of concurrency. All right, so with our perpendicular bisectors here, we see that they are concurrent, right? They are concurrent, they cross at one point. That was the definition of concurrent, three lines that cross at one point. And then we have a point of concurrency. It is that point where all three cross. All right, so we'll get to that name, we'll get to what that's called in a second. But for now, what I want to do is I want to show you on the computer here using a program. Hold on, it's loading. Of course. There we go. Super zoomed in. So on this computer program, and this is easier than me drawing all over the board, we've got a triangle. Okay, here's our triangle. I'm going to have the computer draw in the perpendicular bisectors. So there's a perpendicular bisector. There's one, there's one. As we said, they all cross, they are concurrent. So now I've got this point of concurrency, which I've labeled D. Okay, the computer is going to keep these being perpendicular bisectors. Whatever I do to this triangle, this is always going to be the perpendicular bisector here. Through the midpoint, perpendicular. Here, it's through the midpoint, right? This is the midpoint, perpendicular. Through the midpoint, perpendicular. They're all perpendicular bisectors here. Okay? So let's watch what happens when I move this triangle. Okay? They're always going to stay concurrent. Right? They're always going to cross, no matter what type of triangle I have. Now, all the triangles I've shown you so far have been acute triangles. Watch what happens when we make an obtuse triangle. We make an obtuse triangle, and that perpendicular bisectors, that point of concurrency now is outside of the figure. So they might have to cross outside of the figure. We still have a perpendicular bisector here and here, right? This is a perpendicular bisector of AC, but now we have to go this way to find that point where all three cross. So they could cross inside the figure, they could cross outside the figure, And let's take a look at what happens in a right triangle here as well.
For the obtuse triangle, for the obtuse triangle, is it always going to be, are they always going to cross outside of the triangle?
Yes.
Okay.
Yep. For obtuse, it's always outside. Yep. So let's look at a right triangle. If I look at a right triangle, it's always going to be on the figure. Okay, it's on the figure now. And specifically, it's on the hypotenuse. And even more specifically, it's the midpoint of the hypotenuse. Because I know it has to go, this line has to go through that midpoint. This is the midpoint of that hypotenuse. So in a right triangle, it's pretty easy to find this point of concurrency. It's going to be the midpoint of the hypotenuse. Let's write some stuff down about this. Let's give it a name, and then write some information down. The name of this is called the circumcenter. Okay, this is the circumcenter of the triangle. And what we know, what we just looked at, is that for acute triangles, it is inside the triangle, always inside the triangle. If it's an obtuse triangle, it's always going to be outside of the triangle. And if it's a right triangle, it will be the midpoint of the hypotenuse every time. So this gives us a little bit more information about the circumcenter and where we're going to be able to find it. Because part of what we're going to have to do is to find the circumcenter. And we know we can find it just by drawing in our perpendicular bisectors. But we're going to have to find it in the coordinate plane at the end. And this is going to help to make sure we know what we're talking about. So we've got our circumcenter inside, outside, or the midpoint of the hypotenuse, depending on what type of triangle that you have. We also have a theorem about this, though. And this is, this is how we use the circumcenter, or why it's important to find the circumcenter. In our theorem, called, of course, the circumcenter theorem, our theorem is that the circumcenter is equidistant from the vertices of the triangle. Equidistant from the vertices of the triangle. So let's copy that down. Let's make sure we have it. I would underline the word vertices, just like I have up there. And if you recall, equidistant, right, quite literally means equal distance. So we're saying that the circumcenter, wherever that circumcenter is, it is going to be the same distance from all three vertices of the triangle. The same exact distance from all three vertices. Okay, so let's take a look at that here, because this computer can measure the distance for us. We're going to have it measure the distance from D to A, D to B, and D to C. We see right there, it doesn't have lines drawn in or anything, but that is the distance between our circumcenter and each vertex. Right now it's 3.01. And if I move this triangle, it's always going to stay the same. They're always going to stay equal, even if it's obtuse. They're going to stay the same. Right? So even if it's obtuse, you might think that this letter B over here, this point is further away, but it's not. It is the same exact distance from that circumcenter. Okay, so this distance, this, and this, all the same. That's what our theorem tells us. That's the important part here, is that they're always going to be the same distance away. And that's what you're going to use to solve a bunch of problems later today. Okay, is knowing that those are the same distance away. All right. So now, because of that, we can see real world applications of this. So let's say that we're starting a company. Okay, we're going to sell something good. I can't even think right now. But here's Michigan. It's very accurate, I know. It looks exactly like the state of Michigan. I know. I could be an art teacher. I get it. So we've got the state of Michigan here. Let's say that we want 3 stores. Okay, 3 stores. We're going to have 1 store down here. We're going to have 1 in Lansing. We're going to have 1 down here. Okay, I've got 3 stores, and we need a central office, right? We need a central office, and I want that office to be the same distance away from all 3 points. And more likely here, this would be more like a distribution center, like an Amazon distribution. I got a buddy that works for Meijer. He talks about their distribution centers where everything's located and then they send it out to each store, right? So if we want a distribution center where all of our stuff is located, I want it to be the same distance away from all 3 stores. I don't want to have to drive further to one store than another. Okay, I want to be the same distance from all 3. That's where the circumcenter comes in. So what we would do here is we would treat this like a triangle, find the circumcenter by doing those perpendicular bisectors, and I would find that location that's going to be the same distance from all 3 of those stores. Okay, people do this in the real world. They probably have computers to do it for them, right, to be a little bit more accurate, but that's what the computer is doing for them to be able to find that. And most of the time it's going to be more than 3, right? But you know, we're still in 8th grade here. We're still in geometry, so we're not going to get too crazy. But if we have those 3 stores, we can find that circumcenter is going to find that point that's the same distance away from all 3. Okay. All right. Any questions so far?
Wouldn't it be outside of the triangle because it's an obtuse?
If it's an obtuse triangle, then it would be, yeah. And I think, I don't know, I try not to make it an obtuse triangle because that is less great because you wouldn't necessarily make it down here, right? But yeah, yes, I think that's an obtuse triangle, so I think it would actually be outside. I tried not to make it that way, but it ended up being that way. Any other questions about it? All right, so we have one more thing to fill in on our notes, and then we've got our last type of problem that we're going to look at. So we've got this thing that's called a circumscribed circle. Circumscribed circle. It's easier if you draw the circle first. Draw the circle first and then draw the triangle inside of it. Otherwise, not going to work out too well for you. So this is a circumscribed circle. It's a circle with a triangle inside of it. And all 3 points, all 3 vertices from that triangle are on the circle. They are on the circle. And what we can say about a circumscribed circle is that the center of that circle will be the circumcenter of the triangle. Okay, the center of the circle and the circumcenter of the triangle are the same exact spot, which should make sense to us based on our theorem and our knowledge of circles, because we know that from the center of the circle to any point on the circle, all 3 of those radii are going to be congruent. All right, they're all the same radius. From the center of the circle to the circle, they're all going to be the same. Same thing with circumcenter. We know the circumcenter of the triangle is the same distance away from all 3 vertices. So if both of those happen to be true, that means that has to be the same point, okay, for a circumscribed circle. All right, so you just might see some mention of circumscribed circle. This is what they're talking about when you see that. All right, so let's look at the last type of problem that we're going to see. And I'm going to show you the easy version right now. And then, like I said, I'll put another video up of the harder version of this when I have some more time to really get into it. But we're going to look at the basic version, the easy version of this. And it's finding the circumcenter on the coordinate plane. Finding it on the coordinate plane. Finding the ordered pair of where the circumcenter is supposed to be, given our three vertices, given our triangle. So for all of them, every time you see this type of problem, we're going to want to sketch it out first. Doesn't have to be a perfect drawing, but we want to sketch it out so we can kind of visualize what's going on. I've got 0, 3, I got 0, -1, and I got 6, -1. Okay, so I've got this triangle, and I want to find the circumcenter of it. Now, some of you might be able to see and think about why this is considered the easy problem, the easy version of this. Is the easy version because it's a right triangle. Because it's a right triangle, remember we said the right triangle, the circumcenter is going to be the midpoint of the hypotenuse every time. So this is going to be nice and easy because all we have to do is find the midpoint of that line. So I take my points A and C, because this was A, this was C. I find the midpoint between A and C, and I've got my answer. Okay, that gives me that circumcenter. Okay, which if I were to draw in my perpendicular bisectors here, they would cross at that point. 3, 1. That's the midpoint, that's my circumcenter. Okay, that gives me that nice easy answer when it's a right triangle. When it's not a right triangle, and again, I'll get into this a lot more on my other video or later today, this afternoon, if you want to join the Zoom this afternoon. Let's say that I have this triangle instead, and it's not a right triangle. Well, now I need to figure out 2 of my perpendicular bisectors and where they're going to cross. So this brings in creating equations like we did yesterday, right? Equations of perpendicular bisectors. I said that would be important. So we're going to have to create equations for those perpendicular bisectors. And then once we have 2 of them, figure out where they cross, that's going to get into systems of equations. So we're bringing some algebra stuff back into it. It's a little more intense, right, than just find the midpoint. So be on the lookout for that, or join the Zoom this afternoon, and we'll talk about it. I'll answer all the questions and everything that we have on it. Okay. Any questions right now on what we did talk about?